March 23rd, 1944, 31,000 feet above the Ruhr Valley, the air was thin enough to kill. Second Lieutenant James Harker felt his oxygen mask frost against his face as he pushed the throttle of his P-47D Thunderbolt forward, chasing a pair of Focke-Wulf 190 as that danced just ahead, their radial engines clawing for altitude in the crystalline morning light. The German fighters climbed with the confidence of predators who owned this particular piece of sky. At 30,000 feet, the Fw-190 had always held the advantage, its BMW 801 engine delivering consistent power where American fighters gasped and shuddered. But on this morning, something was different. Harker's Thunderbolt callsign Jersey Bounce didn't falter. It didn't wheeze or shake as it had on 100 previous missions. Instead, the Pratt and Whitney R2800 double Wasp roared with an authority that seemed impossible at this altitude. The Supercharger, that massive turbine buried in the fuselage behind him, was spinning faster than Republic Aviation had ever intended. It was feeding his engine compressed air at a rate that would have made factory engineers blanch. And it was the result of a modification that officially didn't exist. 3 weeks earlier, a Technical Sergeant Michael Mickey Novak, a pre-war motorcycle mechanic from Youngstown, Ohio, had done something the manual explicitly forbade. Working alone in a freezing maintenance tent at RAF Boxted in Essex, he had adjusted the wastegate actuator on Harker's P-47, changing the boost pressure curve in ways that violated every specification Republic had published. Novak hadn't asked permission. He'd simply listened to pilots complaining that German fighters consistently outclimbed them above 25,000 feet, studied the turbocharger blueprints until his eyes burned, and made a choice. Now, as Harker closed the distance to those Focke-Wulfs, that choice was proving itself in the only laboratory that mattered. The altimeter needle trembled past 32,000 feet. The Fw-190s began their usual tactic, a steep climbing turn designed to force pursuing American fighters into a stall. But Jersey Bounce didn't stall. It climbed, and kept climbing. The German pilot in the lead aircraft must have glanced back, seen the Thunderbolt still there, still rising, and felt the first cold touch of disbelief. In combat reports filed later that week with Jagdgeschwader 1, Luftwaffe pilots described American fighters demonstrating unexplained high-altitude performance inconsistent with known specifications. One report noted with careful precision, enemy P-47 maintained pursuit to 33,000 feet without visible loss of power. Previous encounters indicated performance degradation above 28,000 feet. What those German pilots were witnessing was the culmination of a problem that had plagued American fighter operations since 1943. The issue wasn't the airframe. The P-47 Thunderbolt was a magnificent piece of engineering, 7 tons of riveted aluminum and firepower built around the most powerful radial engine ever fitted to a single-seat fighter. The R2800 delivered 2,000 horsepower at sea level, an astonishing figure. But power at sea level meant little in the war being fought 6 miles above Europe. The challenge was oxygen, or rather, the lack of it. At 30,000 feet, atmospheric pressure drops to roughly 30% of sea level values. An engine is essentially an air pump, and without sufficient air density, combustion falters, fuel burns incompletely, power drops catastrophically. The German solution had been elegant. The BMW 801 radial in the Fw-190 used a mechanically driven supercharger that provided forced induction across the entire altitude range, delivering consistent boost pressure even where the air grew impossibly thin. The American approach was different and, on paper, superior. The P-47's General Electric turbo supercharger was driven not by the engine's crankshaft, but by exhaust gases. Spinning at speeds exceeding 20,000 revolutions per minute, the turbine compressed incoming air before it entered the engine's cylinders. This system was theoretically more efficient, extracting energy from exhaust that would otherwise be wasted, but theory and combat reality often diverged. Republic Aviation's engineers, working from facilities in Farmingdale, Long Island, had designed the turbocharger system with specific operational limits. Maximum boost pressure was set at 52 inches of mercury, a figure determined by metallurgical constraints and thermal stress calculations. The wastegate, A valve that controlled how much exhaust gas spun the turbine was calibrated to open progressively as altitude increased, preventing overboost conditions that could destroy the engine. Every P-47 that left the factory carried these settings, locked in by brass actuators and mechanical linkages that mechanics were explicitly forbidden from adjusting. The problem emerged gradually through combat experience. Pilots returning from missions over Germany reported consistent patterns. Below 25,000 feet, the P-47 could match or exceed any German fighter. Its dive speed was unparalleled, its 850 caliber machine guns delivered devastating firepower, and its rugged construction brought pilots home, even after absorbing punishment that would have disintegrated a Mustang or Spitfire. But above 28,000 feet, the Thunderbolt's climb rate deteriorated sharply. German fighters exploited this weakness ruthlessly. Major Francis Gabreski, who would finish the war as one of America's top aces with 28 confirmed kills, described the frustration in his combat diary. The Hun knows our ceiling limitations. Fw-190s and Mi-109s routinely climb above 30,000 when engaged, forcing us to break off or follow into an energy-depleted state. We arrive slow and vulnerable. They dive at will. 8th Air Force bomber crews paid the price, flying their B-17s and B-24s at altitudes between 25 and 28,000 feet. They depended on fighter escorts to keep German interceptors at bay. When those escorts couldn't follow enemies into the thin air above, bombers died. The arithmetic was brutal. In October 1943, during the disastrous Schweinfurt-Regensburg raids, the 8th Air Force lost 60 B-17s in a single day, primarily to German fighters attacking from high-altitude positions where P-47 escorts couldn't effectively engage. This was the problem Mickey Novak inherited when he arrived at RAF Boxted in January 1944. Novak was not an engineer. He had no formal education beyond high school, but he possessed something equally valuable, an intuitive understanding of internal combustion engines developed through years of coaxing performance from machines that weren't supposed to deliver it. In civilian life, he'd built racing motorcycles that won on dirt tracks across Ohio. He'd learned to read an engine's personality through subtle variations in sound and vibration, to understand what metal could tolerate and where tolerances could be pushed. The P-47's turbocharger fascinated him. During his first week at Boxted, while other mechanics focused on routine maintenance, Novak studied the system obsessively. He examined technical manuals, cross-referenced them with field modification bulletins, and, most importantly, he listened to pilots. What emerged from those conversations was a clear pattern. The factory wastegate settings were conservative, optimized for engine longevity and foolproof operation rather than maximum performance. At high altitude, the wastegate opened too early, limiting boost pressure precisely when pilots needed it most. Novak's insight was simple but radical. The engine could handle more. The metallurgy was sound. Pratt and Whitney had built the R2800 with generous safety margins, knowing it would be operated under combat stress by pilots with varying skill levels. The limiting factor wasn't the engine's physical capacity, but rather Republic's institutional caution. If the wastegate could be adjusted to stay closed longer at altitude, allowing the turbocharger to spin faster and deliver higher boost pressure, the engine would produce significantly more power where it mattered most. The modification itself was mechanically straightforward. The wastegate actuator used a system of springs and levers connected to an aneroid capsule that sensed atmospheric pressure. By carefully bending the actuator arm and adjusting spring tension, Novak could alter the pressure curve, delaying wastegate opening until higher altitudes. The work required precision, but not exotic tools. In the dim light of the maintenance tent, using hand files and feeler gauges, he could recalibrate an entire turbocharger system in about 4 hours. What made the modification forbidden was not technical difficulty, but organizational reality. The Army Air Forces operated under strict technical orders. Modifications to critical engine systems required written authorization from right field engineering staff exhaustive testing, and formal approval through channels that could take months. Frontline mechanics were permitted to perform only approved maintenance procedures detailed in technical orders. Deviating from those procedures could result in court-martial if something went wrong. Novak understood the risk, but he also understood that the pilots he served were dying in a war that wouldn't wait for bureaucratic approval. On the night of February 28, 1944, he made his decision. Lieutenant Harker's P-47, Jersey Bounce, would be the test case. Harker was a skilled pilot, cautious but aggressive when necessary, someone who would notice performance changes and report them honestly. If the modification worked, Novak would expand it quietly to other aircraft. If it failed catastrophically, the consequences would fall on him alone. The first test flight occurred on March 2nd. Harker took off from Boxted's grass runway in morning fog, climbed to 30,000 feet over the North Sea, and pushed the throttle forward. His post-flight report was terse but telling. Engine performance noticeably improved above 28,000 feet. Climb rate sustained to 32,000. No unusual vibration or temperature anomalies. Request continued operational testing. Over the following 3 weeks, Novak quietly modified 11 more P-47s in the squadron, always working night shifts, always careful to leave no documentation. Pilots began reporting similar results. Aircraft that had previously struggled above 30,000 feet now maintained robust power to 35,000 and beyond. Climb rates improved by an average of 400 feet per minute at altitude, a seemingly modest gain that translated into life or death advantages in combat. The German response confirmed the modification's effectiveness. Luftwaffe combat reports from mid-March began noting anomalies in American fighter performance. A tactical assessment from Jagdgeschwader 26 stated, "Recent encounters suggest enemy P-47 units have received improved power plants or operational modifications. High-altitude engagement is no longer advisable without numerical superiority." But improved performance came with costs that Novak understood better than anyone. The increased boost pressure meant higher cylinder head temperatures, greater mechanical stress on connecting rods and crankshaft bearings, and accelerated wear on piston rings. Engines running the modified settings required oil changes every 15 flight hours instead of the standard 25. Spark plugs fouled faster. Turbocharger bearings spinning at extreme speeds had shorter service lives. What Republic designed to last 200 hours between overhauls now needed inspection every 100. Novak accepted this trade. In his view, an engine that brought a pilot home after 100 hours of brutal service was infinitely more valuable than one that lasted 200 hours in a crashed aircraft. Ground crews adapted, working longer hours, scrounging parts, becoming expert at field repairs that kept modified birds flying. The logistics were punishing, but the results spoke for themselves. The modification's existence remained unofficial, spread through informal networks of mechanics and pilots. Squadron commanders who noticed improved performance wisely chose not to investigate too deeply. This was war, and war rewarded results over procedure. By April 1944, an estimated 40 P-47s across 3 squadrons were flying with Novak's adjustments, though no official record acknowledged this fact. The breakthrough's significance became undeniable on April 15th during a massive bomber escort mission to Berlin. Over 100 B-17s, protected by P-47s and P-51s, penetrated deep into German airspace. Luftwaffe fighters rose to meet them, climbing to 32,000 feet where they expected to hold altitude advantage over the American escorts. Instead, they encountered Thunderbolts that matched their climb, pressed attacks at altitudes where American fighters had previously been impotent, and disrupted formations before they could reach the bombers. Lieutenant Colonel Hubert Zemke, commander of the 56th Fighter Group, noted in his after-action report, "Enemy fighters demonstrated unusual reluctance to engage at high altitude. Several Fw-190 formations broke off attacks when our P-47s maintained pursuit above 30,000 feet. This represents a significant tactical shift." What Zemke's report didn't mention, because he may not have fully known, was that many of his group's Thunderbolts were flying with modified turbocharger settings that existed outside official channels. The performance he observed wasn't the result of new aircraft or factory improvements. It was the work of mechanics like Novak who understood that sometimes the difference between victory and defeat lived in the gap between what regulations permitted and what physics allowed. The modification's full potential revealed itself in combat geometry. Air warfare is fundamentally about energy management. An aircraft's ability to climb, turn, or accelerate depends on its total energy state, the combination of speed and altitude. At high altitude, where air is thin and engines struggle, even small performance advantages compound dramatically. A fighter that can climb 400 feet per minute faster than its opponent doesn't just reach 35,000 feet sooner, it arrives with greater speed, better position, and more options. German pilots had learned to exploit altitude as both shield and weapon. Climbing above 30,000 feet allowed them to observe bomber formations, choose attack vectors, and dive through escort screens with speed advantage. American fighters forced to climb after them arrived slow and vulnerable, easy targets for the high-speed slashing attacks German doctrine emphasized. Novak's modification disrupted this calculus. P-47s that could match or exceed German climb rates eliminated the altitude sanctuary, forcing Luftwaffe fighters to either engage on more equal terms or avoid combat entirely. The psychological dimension mattered as much as the mechanical one. German fighter pilots in 1944 were not the same men who had swept across Europe in 1940 and 41. Years of attrition had claimed the best, leaving younger pilots with less training and more fear. They'd been taught that American fighters had predictable limitations, when those limitations suddenly vanished. When Thunderbolts appeared above them where no Thunderbolt should be, confidence fractured. A captured Luftwaffe pilot interrogated at an Allied POW facility in May 1944 described the shift. "We were told the P-47 cannot fight above 30,000 feet. This information was reliable for many months. Then, in March or April, it changed. The Thunderbolts climbed where they should not. We no longer knew what to believe about enemy capabilities." That uncertainty was itself a weapon. Warfare is as much about perception as reality. If an enemy believes you can reach them anywhere, they must defend everywhere, spreading resources, thin, and surrendering initiative. The modified P-47s created exactly this effect across German fighter commands, yet the modification remained fragile, sustained by informal networks rather than institutional support. Novak's work spread through personal relationships and word of mouth among ground crews. A mechanic from the 56th Fighter Group would transfer to the 78th, bring the knowledge with him, modify a Focke-Wulf aircraft, and performance would improve incrementally. But this organic growth meant inconsistency. Some squadrons flew entirely with modified turbochargers. Others had a handful of improved aircraft mixed with standard ones. Pilots couldn't reliably predict which P-47 would deliver high-altitude performance until they climbed and tested the throttle response personally. This inconsistency created strange battlefield dynamics. German pilots learned they couldn't assume all P-47s were equal. Some climbed aggressively to altitude, others fell behind. Combat reports became filled with hedging language describing American fighters as possibly improved variants or suspected modified power plants. The Luftwaffe's intelligence apparatus struggled to determine whether they faced a new production model or field modifications. And that uncertainty itself degraded their tactical planning. The Army Air Force's official recognition of the modification came slowly and reluctantly. Engineering officers at Wright Field received field reports describing improved high-altitude performance, but initially dismissed them as pilot exaggeration or statistical anomalies. The idea that frontline mechanics were systematically adjusting complex turbocharger systems without authorization was both implausible and troubling from an institutional perspective. Reality forced acknowledgement. By June 1944, enough aircraft were flying with modified settings that patterns became undeniable. Engine failure rates in some units had increased slightly, but combat effectiveness had improved dramatically. Bomber loss rates dropped as fighter escorts provided better high-altitude coverage. Whatever was happening in the field was working, even if it violated procedures. Colonel Cass Hauff, Director of Technical Services for the 8th Fighter Command, ordered a formal investigation. Teams of engineering officers visited frontline bases, interviewed mechanics, examined aircraft, and compiled data. What they discovered was a vast, informal modification network spanning multiple fighter groups, all tracing back conceptually to insights developed by mechanics like Novak, who'd learned to hot rod engines in civilian life. The official response was characteristically bureaucratic, rather than court-martial the mechanics or ground the aircraft. The Army Air Forces retroactively authorized the modification as Field Technical Order 41-47-3, Emergency High-Altitude Power Setting. The technical order specified exactly the adjustments Novak and others had been making for months, now blessed with official approval. Mechanics who'd been working in regulatory shadows suddenly found themselves credited with developing an approved field modification program. Novak himself never received formal recognition. His name appears in no official histories, no awards citations. He was simply a staff sergeant who did his job and moved on when his unit rotated home in August 1944. But his legacy lived in every P-47 that climbed to 35,000 feet over Germany, in every bomber crew that made it home, because fighter escorts could reach attackers that once operated with impunity. The modification's broader significance extended beyond individual combat encounters. It represented a distinctly American approach to technological warfare, pragmatic, iterative, and willing to empower frontline personnel to solve problems without waiting for hierarchical approval. German and British military systems, bound by more rigid engineering protocols, rarely permitted such informal innovation. American mechanics, drawn from a culture of automobile tinkering and self-reliance, brought different assumptions about what rules could be bent in service of effectiveness. This cultural dimension mattered strategically. Germany's aircraft industry, in 1944, was producing technically sophisticated machines, fighters with pressurized cockpits, advanced fuel injection, and refined aerodynamics. But German doctrine didn't encourage or trust field modifications. Mechanics followed technical manuals precisely, and deviations were punished. The Luftwaffe thus operated with the performance their factories delivered. No better, no worse. American forces operated differently. A mechanic who saw a problem and knew how to fix it was expected to try, within reasonable bounds. This created chaos for logistics and quality control, but it also meant that American combat units evolved faster than adversaries could track. The P-47 that fought in June 1944 was functionally different from the P-47 of January, not because factories had changed production models, but because ground crews had collectively improved what factories delivered. The technical principles underlying Novak's modification were eventually incorporated into later P-47 production models. The P-47M and P-47N variants featured turbocharger systems with revised wastegate actuators that delivered higher boost pressure at altitude as standard equipment. But these improved models didn't reach frontline units in significant numbers until late 1944. Long after, mechanics like Novak had already solved the problem with hand tools and determination. Combat effectiveness data tells the story in numbers that even institutional skeptics couldn't dismiss. Between March and June 1944, fighter groups using modified P-47s reported a 23% increase in enemy aircraft destroyed at altitudes above 30,000 feet, compared to the previous 3-month period. Simultaneously, bomber loss rates in missions those groups escorted dropped by 17%. The correlation wasn't perfect. Many factors influenced aerial combat outcomes, but the trend lines were compelling. German production data reveals the modification's strategic impact from another angle. In early 1944, German factories prioritized building Fw-190s and high-altitude interceptors specifically designed to exploit American fighters' altitude limitations. By summer, those priorities shifted toward lower-altitude, ground attack aircraft and jet fighter development. The Luftwaffe's command structure had concluded that conventional high-altitude fighter tactics against improved American escorts were no longer cost-effective. This shift represented a fundamental victory achieved not through superior numbers or brute force, but through mechanical cleverness and willingness to break rules intelligently. A modification that took 4 hours to perform in a freezing maintenance tent helped reshape German strategic aviation priorities. Individual pilots felt the impact most directly. Second Lieutenant James Harker, whose P-47 Jersey bounce was the first to receive Novak's modification, survived the war with 11 confirmed aerial victories, 7 of which occurred at altitudes above 30,000 feet. In his post-war memoir, he devoted an entire chapter to the mysterious performance improvement his aircraft received in March 1944. "I never knew exactly what Mickey did to that engine," Harker wrote. "He'd just smile when I asked and say something about adjusting the mixture. But whatever it was, it saved my life, at least twice. There were days when being able to climb another 1,000 feet faster than the guy chasing me was the only reason I made it home for dinner." Other pilots shared similar experiences. The modification created a category of aerial combat that hadn't existed before: high-altitude dogfights, where American fighters could compete on equal terms. Previously, encounters above 30,000 feet had been brief and desperate, American pilots trying to get shots off before their aircraft stalled and fell. After the modification, those encounters became genuine tactical engagements where skill and tactics mattered as much as raw performance. The Luftwaffe adapted slowly, but inevitably. By August 1944, German tactical doctrine explicitly discouraged high-altitude interception of American fighter-escorted bomber formations. New pilots received training emphasizing low-altitude attacks, ground control intercept coordination, and jet fighter tactics that bypassed the altitude question entirely. The Me-262 jet, entering service that summer, rendered the entire high-altitude piston engine competition obsolete. But the Me-262 came too late and in too few numbers to alter strategic outcomes. The period between March and August 1944, when modified P-47s dominated high-altitude battles, coincided with the Allies' critical build-up for D-Day and subsequent European campaigns. Air superiority achieved during those months enabled invasion preparations and close air support operations that ground Wehrmacht forces found overwhelming. The story of Novak's modification illustrates a broader truth about warfare and innovation. Technological advantage is rarely static. It exists in the continuous tension between what equipment can theoretically do and what operators can make it actually do under combat conditions. Factories produce potential. Frontline mechanics and pilots convert that potential into capability. Republic Aviation's engineers had designed the P-47's turbocharger system with specific performance parameters based on laboratory testing and theoretical calculations. Those parameters were conservative, optimized for reliability across the widest possible range of conditions and pilot skill levels. Novak and mechanics like him recognized that combat operations could accept narrower reliability margins in exchange for higher peak performance. They shifted the balance, trading long-term durability for short-term tactical advantage. This trade-off wasn't reckless. It was calculated risk management by people who understood both the machines they maintained and the tactical realities their pilots faced. An engine that failed after 100 hours of modified operation was still infinitely preferable to one that lasted 200 hours in a hangar after its pilot died. In combat at 30,000 feet. The modification's success depended on multiple enabling factors that came together fortuitously. American industrial capacity meant replacement engines and parts were abundant enough to sustain higher maintenance tempos. The Army Air Force's relatively decentralized command structure gave squadron leaders discretion to tolerate unofficial modifications if results warranted. And American mechanical culture, steeped in hot rod tradition and shade tree engineering, produced a generation of mechanics who viewed technical manuals as suggestions rather than absolute limits. None of these factors alone would have mattered. Germany had skilled mechanics. Britain had decentralized command structures in some contexts, but only the American military system in World War II combined all three elements consistently enough that informal innovation, like Novak's, could flourish and spread across multiple units without triggering institutional suppression. Standing on the flight line at what was once RAF Boxted, now a quiet English farmland, the ghosts of that innovation are difficult to perceive. The concrete runways have been torn up, the maintenance tents are long gone, and the roar of R2800 engines is just memory. But the principle those mechanics demonstrated remains vivid, that sometimes the most sophisticated military technology in the world still depends on a man with a wrench who knows when rules serve mission and when they don't. The P-47 Thunderbolt entered combat as a capable but limited fighter, hamstrung at high altitude by conservative engineering. It evolved into a devastating high-altitude weapon, not because factories improved it, though later models did incorporate lessons learned, but because mechanics in frozen tents refused to accept limitations they knew could be overcome. That refusal, multiplied across dozens of maintenance crews and hundreds of aircraft, changed the character of aerial warfare over Europe in ways German commanders struggled to understand or counter. The forbidden supercharger trick wasn't really forbidden by physics or engineering. It was forbidden by regulations, written by people who weren't there, who hadn't watched bombers fall from the sky, while escorts helplessly watched from lower altitudes. Novak's genius lay in recognizing that distinction and acting on it, accepting personal risk to solve a problem that institutional processes were too slow to address. In the final accounting, the modification represented something quintessentially American in its approach to warfare. Practical, improvisational, and focused relentlessly on results rather than procedures. It embodied the belief that soldiers closest to problems often see solutions invisible to distant authorities, and that victory sometimes requires trusting those soldiers to color outside the lines when circumstances demand it. The German officers who reviewed combat reports describing P-47s climbing to 35,000 feet didn't freeze from fear. They froze from recognition that they faced an adversary whose technological edge wasn't just in what factories produced, but in what mechanics and pilots did with those products once they reached the battlefield. That edge, built on wrenches and determination rather than blueprints alone, proved as decisive as any weapon system. Years after the war, a journalist tracked down Mickey Novak at his motorcycle repair shop in Youngstown. She asked if he'd known his modification would make such a difference. Novak's answer was characteristically modest. "I just figured if we could get the engines to breathe better up high, the pilots might come home more often." Seemed worth trying. That simple pragmatism, multiplied across thousands of maintenance decisions made by mechanics across the European theater, constituted a form of innovation that no research laboratory could replicate. It was innovation born from necessity, executed with hand tools and spread through networks of trust rather than official channels. And it worked precisely because the men who performed it understood both the machines and the human cost of accepting limitations that could be overcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.